All right, this is 2017 number 5. It gives us a little combustion reaction here. Combustion reaction because oxygen is a reactant. This is propanol. That's there. And so we got a balanced equation. We'll see if that comes into play at all when we need that mole to mole ratio or not. Basically, we got this set up where we've got some propanol that's burning. This wick is pulling the propanol up through capillary action. It's burning and it's heating up some water above that propanol. And so they're asking us some questions about how much heat is being taken in by the water here. And so it gives us some data. Mass of the propanol that's combusted, mass of the water that's heated, initial temperature, final temperature, specific heat of water, 4.18, which we already kind of have memorized anyway. And so you see specific heat formula or constant somewhere, then you know you're dealing with Q equals MCAT, and that's what we're doing here in A. A says calculate the magnitude of the heat energy absorbed by the water. So if we're looking at energy by the water, that means that we are using the specific heat constant of water. So this is Q equals MCAT on A. I've decided to be the man of many different pen colors. So I'm going to try to switch pen colors all the time just for funsies. So 5A, Q equals MCAT, where we are looking for Q, the amount of energy that is absorbed by that water. So we have a mass. If it's specific heat constant of water, we need the mass of water. They gave us the mass of water, 125.00 grams times the specific heat constant, the 4.18. Be so careful of your units here. Make sure they didn't give you this unit in joules or kilojoules and ask for the other one. You have to be careful here. This one asks for the energy, if you look, in kilojoules, and so don't get caught. This is joules over grams times degrees Celsius. And that's our constant times the change in temperature. We have 51 as our final temperature, 22 our initial temperature. Subtract those and we should get a positive amount of heat gained. 29.1 degrees Celsius. Gas laws we always do in Kelvin. This is a change in temperature, and the change in Celsius is exactly the change in the temperature in Kelvin. So it doesn't matter whether these are in Celsius or Kelvin. That unit's going to cancel out anyway. And so Q here, when we punch this in, gives us 15,205 joules of heat that was absorbed by the water. They want the answer in kilojoules. You have to put it into kilojoules. It's 15.2. You don't need to show a conversion there. Kilojoules of energy that was transferred. That's part A. Just like that. Easy enough. Part B says, based on the experimental data, if 1 mole of propanol was combusted, how much heat in kilojoules is released? Report your answer correct number of significant figures. Okay, that matters here in this thing. And so here we go. Because they said the right number of sig figs, you got to make sure you put in the right number of sig figs or you'll get caught. They're actually giving you a point for that, which is really nice. So what we've got here is not a full mole of propanol. We only have 0.55 grams of propanol that was burned. And so we need to figure out how much energy is going to be given off by that 1 mole of propanol. So what I did is I took our 0.55 grams of propanol, C3H7OH, and I turned it into the number of moles of propanol that I burned up here. Because if this much is gained by the water, then that much was given off by that much of the propanol. So I'm going to go grams to moles here. I add that guy up, I get 60 grams per 1 mole. And that tells me that my moles of propanol here are 9.2 times 10 to the negative third moles. Now I tell you guys go to the 3 sig figs all the time, except this one specifically asks about sig figs. I only have 2 here, which means I can only have 2 here for my moles of propanol. And if I want to figure out how many kilojoules per mole, that's what B's asking, how much heat in kilojoules per mole is released per 1 mole, all I have to do is deal with the units that I've got handy there. My units, it's 15.2 kilojoules of energy were given off by 9.2 times 10 to the negative third moles of that propanol. And I divide those guys up. 3 sig figs, 2 sig figs. My answer here should just have 2 sig figs. I got 1700 kilojoules per mole of the C3H7OH. That's my answer. You get a point for, let's double check. You get a point for the correct amount of heat released, and then you get a point for recording the answer the correct number of sig figs based on that data. That's it on B. So you get 2 points for B. And then part C says a second student performs the experiment using the same mass of water, same initial temperature. However, the student uses an alcohol burner containing the propanol that has water in it, which is miscible, so they dissolve in each other. The difference in the mass of the alcohol burner before and after the combustion is also 0.55, with the final temperature of the water in the beaker heated by the alcohol burner in this experiment greater than, less than, or equal to the final temperature. This is one where you're looking for some kind of trick in this. There's no trick here. In the top part, this was 0.55 grams of pure propanol giving off that heat. If you mix in water with it, then that 0.55 grams also contains some water, and that water is not combusting, and so it's not producing any more energy. So overall, you're going to have less. Make sure you're answering the question. The question is, would the final temperature of the water be less than, equal to the final temperature? It would be less than. Because the water is not combusting to release heat, or less propanol is combusting. You may put temperature is less than. Temperature change is less than. That's it on number 5. It's a Q equals MCAT problem. Q equals MCAT has shown up on the last 6 or 7 straight years of the AP exam, so I don't doubt that you'll see it again. This conversion happens a lot too, that kilojoules per mole. All right.